We're now going to go over how to graph motion. What does that mean? Well, if you're graphing a distance time graph, a velocity time graph, acceleration time graph, what do those look like and which ones correspond with the other? So, a few things you need to know before we go over that. The slope of a distance time graph is speed. Slope of a displacement time graph is velocity. Okay, sometimes they're one and the same if it's just going the same direction the whole time. But if we have a displacement time graph that is curved, that means that we have acceleration happening. So if you want to know, is this velocity going up or down, we're going to draw a tangent line. What is a tangent line? A tangent line is something that touches a curve at only exactly one point. So say I have a curve like that, a tangent line, if I just want to touch it right there, it'll just be a line that goes right like that. Okay, any other line will either not go through that curve or touch it at 2 points. So we're just looking for a line that touches that curve at 1 point. And then you're going to look. Is it a positive slope? Is it a negative slope? Are the slopes getting bigger or are they getting smaller? And that's going to tell you if something's speeding up or slowing down or something like that. The slope of a velocity time graph. So there's our distance time graphs and our displacement time graphs and the information we can gain from that. Okay, so we can tell if it's constant velocity or not. We can tell what the velocity is by finding the slope. And if it's a curved line, then we know it's accelerating. So slope of a velocity time graph is now acceleration. So that's how we're going to get acceleration from a velocity time graph. There's one other thing we can get from the velocity time graph, and that's the area between the velocity time graph and the x-axis, and that's going to be displacement. So don't worry, we're going to go over all those examples and how to figure out all that stuff, because I know that's a lot of information just on this one slide. But before we do that, I just want to look at the different types of relationships in the graphs that we can have. And if you have a certain distance time graph, what would that look like on a velocity time graph or an acceleration time graph? So here, I'm going to draw a distance time graph, and then we're going to figure out what the corresponding velocity and acceleration time graphs would look like. So say I had a distance time graph that looked like that. It's supposed to be a straight horizontal line. It went up a little bit, but it's not meant to be. Unfortunately, it's difficult to use a ruler on here, so I'm just not going to. So that's a horizontal line. So what does that mean? It means you're not covering any distance, right? If you're not covering any distance, what does that mean for velocity? Well, it means your velocity is just constant at 0, because it just means you're staying in the same place. If you're staying in the same place and you're not moving, then can you even have acceleration? No, so your acceleration is also just a line at 0. Okay, nice and easy. Now one that you've seen a bunch is a distance time graph like this. Or displacement time, doesn't matter. So what is this? This is that uniform motion, isn't it? Your displacement is changing consistently over time. So what does that mean for our velocity when our displacement time graph looks like that? Well, it's starting at 0 and it's getting farther away. So that means we have a positive velocity going in a positive direction. It also means this velocity is constant, okay? So as you can see, you probably haven't seen many velocity time graphs like this, but I have 0 and I have space below 0 to draw something if I want. But here I know it's starting at 0 and it's getting larger, the velocity. So I know that my velocity is positive and going in a positive direction. So it's going to be above 0, but it's going to be constant. It's going to be a horizontal line because the velocity is not changing. And since the velocity is not changing, is the acceleration changing? Absolutely not. Another way to think about this, how do I go from a distance time graph to a velocity time graph? Remember, this slope here is equal to your velocity. So if I look at the slope, it's going to be a nice constant positive number, because when a slope goes that way, it's positive, okay? And when a slope goes this way, it's a negative slope, right? Because it's generally going down. So I know if the slope's going like that, then it's a positive slope, so my velocity is going to be positive and constant. Okay? And then the slope of velocity time graph, this slope is your acceleration. What's the slope of a horizontal line? It is absolutely 0. Okay? Let's move on. So what if my displacement time graph looks like this? That's still uniform motion, right? Because it's a straight line. But now we're going from not 0 to 0. Also, it's going this way, so that means my slope is negative, which means my velocity should be negative. But it's still constant because that's a nice straight line, which means a uniform motion for us. So it's just a constant negative velocity is all that's happening because they're moving backwards. And if our velocity is constant, do we have an acceleration? Absolutely not. So that's still just a line right there at 0. Okay, let's get into a few more interesting scenarios. What if my distance time graph looks like this? Okay, we are obviously out of the realm of uniform motion. Okay, this is telling you that something is speeding up or slowing down. The velocity is changing. So the question is this thing getting faster or slower? So this is where the tangent lines really help you, okay? Take a point at the very beginning and draw a tangent line. So again, it should only touch that one point on the curve and no other point, okay? Do the same at the end when the time is larger. Draw another tangent line. What's happening? That slope is getting larger, is it not? Because when you have a steeper slope like this is a larger slope, and this is a smaller slope. So in fact, this slope is actually, if you were to draw a tangent line right there, that is perfectly horizontal. So this velocity is actually going from 0 and it's getting larger and it's getting more positive because it's going that way. It's generally going up when you look from left to right. So what's happening? This velocity is starting at 0 and it's getting larger. So that's what my velocity time graph will look like. Okay, so this distance time graph is the distance time graph of something that is speeding up. Okay, let's get rid of all this mess that I made here just so we can have a nice clear picture of what it looks like again. So remember, something like this, that's telling you that that is a graph of something that is speeding up. Okay? What will the acceleration time graph look like? Well, we know it's not going to be at 0 now because there is actual acceleration happening. So remember, the slope of a velocity time graph will tell us our acceleration. So you have to ask yourself, is this a positive slope or a negative slope for the velocity time graph? It is positive because it's going up when you look to the right. So that means our acceleration is positive. So it's going to be a nice constant positive acceleration. We're at this point never going to go over a situation where we don't have constant acceleration. So lucky us. Let's go over another scenario. So I'm going to throw at you another distance time graph and you're going to have to figure out what the heck's going on. Okay, something like that. What is happening there? Well, again, tangent lines do help. So what's happening? At this point right here, let's draw our tangent line. Oh, it's a really steep positive slope. And as we go on, what's happening? It's a not as steep positive slope. So we're going from a very, very steep, large positive slope to a small positive slope. So that just means our velocity is remaining positive, okay, above 0. That's all that means. And this also then means that it's doing what? It's slowing down. Because our slopes are going from large to small, right? Because when we have a really steep line, that's a large slope. When we have a shallow line that's getting close to being horizontal, that is a small. slope. So what's happening to our velocity? Well, we're starting large, right, above 0, and we're going down to 0, right? Because again, this is getting smaller and smaller and smaller. It's getting closer to 0 until we get to the end here where it's practically horizontal. So therefore, our velocity is getting slower. Okay, and then what's happening with our acceleration? Well, remember, we want to figure out what is the slope of the velocity time graph. So at this point, I'm not even worried about numbers. I just want to know generally what it looks like. So this, as you go from left to right, this slope is going down. So that means we have a negative slope, which means we have a negative acceleration. So again, this acceleration is going to be constant. We're never going to have one that's vertical or not vertical, but diagonal. We're only going to have horizontal accelerations because they're going to be constant. But there we go. It's a negative acceleration, and we know that because the slope is negative on the velocity time graph. Okay? We also know that because our velocity is positive and it's slowing down, so our acceleration has to be negative. Remember, that's the what happens when something's slowing down. The velocity and the acceleration have to have the opposite signs. Okay? Next scenario, let's say it looks something like this. What the heck is happening? Right? So again, look at your tangent lines. They really, really do help. So we are going from tangent line right here. That pretty much looks like a horizontal line to me. So that's a slope of 0. And then if we go down here, what's happening? That looks like a much steeper slope, but is that a positive or a negative slope? That's a negative slope. Okay, so we're going from a slope of 0 to a large negative slope. So remember, slope tells us what's happening to the velocity. So what this is telling us is that here velocity is equal to 0. Here it's telling us that velocity is equal to some negative number. Okay? And that's what it's telling us. So it's telling us that velocity is starting at 0 and it's getting to be a larger negative. So it looks like it's probably doing something like that. Okay? Because it technically is still speeding up, right? The negative just tells us the direction that it's going. So the velocity is going from 0 to a larger velocity. It's just going backwards. And that's all it's saying. We can also see that because, look, the displacement at the beginning is away from its starting point. At the end, it's at its starting point, right? So that means it's going backwards. What does that mean for our acceleration? So again, I'm looking at this and going, is this a positive or negative slope? Look at this, it's going down as you look from left to right. So therefore, that is a negative slope. So that's our acceleration time graph, the corresponding. Also makes sense. We know this thing is speeding up backwards, so therefore, if it's speeding up and the velocity is negative, then the acceleration also must be negative. Okay, 2 more scenarios. So what if my displacement time graph looks something like that, huh? What do you think that means? So again, let's look at our tangent line. So at the beginning, tangent line is really steep, and it's also negative. And at the end, my tangent line is getting close to being horizontal. Okay? So it's still negative, but it's getting less and less negative, and it's getting closer to horizontal. So what does that mean? It means we have a large negative velocity at the beginning, and we have a velocity of 0 at the end. So what does that mean for our velocity time graph? Well, where is a large negative velocity? Probably down here, right? And then, of course, it's going towards 0, so it's doing that. Okay? So this is the graph of something that is slowing down, but with going backwards, right? It's slowing down backwards, or it's slowing down in the negative direction. And we also, again, know that because it starts away from its starting point and ends at its starting point. Okay? So that is what that velocity time graph would look like. And again, we need to look at that, the slope of that, to get our acceleration. So this velocity time graph is going up, as we look at it from left to right, so therefore it's a positive slope, so therefore our acceleration is positive, okay? It also makes sense if you think about the fact that this is slowing down and it has a negative velocity. So if it's slowing down, the velocity and acceleration have to be opposite signs. So since the velocity is negative, the acceleration must be positive. One more of these. This one's a really tricky one. What the heck are we going to do with this? Okay, so what if my graph looks like this? Again, let's look at the slopes of our tangent lines, and then that's going to help us figure out what the heck's going on here. So we start with a really, really steep tangent line that's positive. Ooh, okay, so that's a large positive velocity. And as we go along, we get to this point right here. What is that? That looks like a horizontal line. Okay, so I'm guessing that at that point, it's at 0, right? The velocity is at 0. So we're going from a large positive velocity to a velocity of 0. And then what's happening near the end here? That is a large negative velocity, right? Because we have a really steep slope. It's going down, so it's negative. So we're going from a large positive velocity to 0 to a large negative velocity. Okay, so let's kind of map out what we think that'll look like. So we know it's starting at a large positive velocity, so up there it's going to go through 0 at some point, and it's going to end at a large negative velocity. So it kind of looks like it'll probably do something like this as time goes on. Okay, does that make sense? Hopefully. Think about it for a few minutes because it does take a little while to get used to that. But really, we know that if something's leveling out like this, that means it's slowing down. If it's getting steeper, it's getting faster. So really, this is just saying something slowed down and then started going in the opposite direction. Acceleration time graph. Again, just look at the slope here. The slope is a negative slope for the velocity time graph. It's going down as you look from left to right. So I just know that the acceleration is negative. Okay, and that's that for graphing and what different graphs look like when they correspond. Okay? So here's an example of a straight displacement time graph. Sometimes it's labeled distance, sometimes it's labeled displacement, sometimes it's labeled position. Just because it's labeled distance time does not mean that it's automatically a scalar, because if it's a distance time graph but you see something going backwards with a negative slope, it's actually displacement time, which I know is really annoying, but that's how life works. So in this situation, we see a negative slope, so we know that this is still definitely talking about vectors, because if something's going backwards or has a negative slope, it means it's going backwards, okay? Or it's going in a negative direction. So just remember with the curved displacement time graph, that's when we know we do not have a acceleration of 0. That's when acceleration is going to be greater than 0 or less than 0. And of course that depends on whether it's speeding up in the positive direction, speeding up in the negative direction, slowing down in the positive direction, slowing down in the negative direction. There's so many different things here. But again, always look for those tangent lines. So as soon as you see a displacement time graph, draw a tangent line down here, draw one up here to really get an idea of what's happening to the velocity. So let's do an example here. Take a look at this, this graph and try to figure out, when does it have no velocity? When does it have no acceleration, like 0 acceleration? When is the speed increasing and when is it decreasing? So I'd like you to actually pause, please, and try to do these on your own. Okay, I'm assuming you paused and you've done these and you're just waiting for me to tell you the right answer. I bet you anything you all got right when there's 0 velocity. It's when it's here, 4 to 6, right? We know that. We know that when there's a horizontal line, it's not moving on a displacement time graph. When is there 0 acceleration? Remember, that's 0 acceleration means that there's uniform motion. So that's usually when we have straight lines on displacement time graphs, or it is. So there we go. There's our nice straight line from 0 to 4. That's nice uniform motion. So that is 0 acceleration. Technically, if you wanted to put, well, actually, what about 4 to 6? Is that 0 acceleration? It is. I know it's 0 velocity, but guess what? 0 velocity still means 0 acceleration. So the most correct thing to put here would be 0 to 6 seconds for 0 acceleration. When is the speed increasing? So remember, that's when your tangent lines are going from shallow to steep. So when the speed is increasing, if you look here, so I know this is going to be this whole curvy thing. So what's happening here? We have a really high speed going to a speed of 0, going back to a really high speed. Okay? So 6 to 8 is going from high speed to 0. So that's actually decreasing speed. So therefore 8 to 10 is when we are increasing speed. And 6 to 8 is when we are decreasing in speed. Okay? Another example, I want to determine the total displacement with this graph. How do I do that again? Okay, well, at the beginning, I did tell you this. How do you find displacement with a velocity time graph? You find the area between the curve and the x-axis. That is so important, okay? What's the curve? It's these lines. This is the curve. Here it's just more boxy and a bunch of lines. Okay, so I need the area of this bit, but I have to stop at the x-axis right here. Don't go all the way down to -4. I don't care that there's a line drawn there. You have to stop. Okay? Now, what do we do when we need to find the area of something like this? It's called a trapezoid, this 0 to 6 seconds thing here. You break it up into shapes that you know how to find the area of. So I have a triangle there, I have a square here, and I have another triangle right here. So I'm actually going to find the area of those three. And then when it goes below the x-axis, guess what? I still can find the area between the curve and the x-axis. It's just the area now happens to be above the line, right? So always stop at this x-axis. I've seen so many people wanting to find all this area. I don't care about that area. That area is telling me nothing because there's no part of the graph there. It's always underneath the curve. Stop at the x-axis unless it's negative, and then you go above the curve to the x-axis. So I'm going to call this area 1, area 2, area 3, and area 4. Okay? So if I want the total displacement on this velocity time graph, I'm just going to find the area between the curve and the x-axis. Okay? So how do you find the area of a triangle? You should have that memorized. Base times height divided by 2, or 1/2 base times height. So we'll do that for the first, and then we have a square, so that's just going to be base times height. And then we have another triangle, so 1/2 base times height. And then we have another triangle, 1/2 base times height. Okay? But of course, they're all going to be different. So for the first triangle, we have the base. It's going from 0 to 2, so that is 2 seconds. My height is going from 0 to 2 as well as velocity, so that's 2 meters per second. Great, okay. And then we have base times height again. So this goes from 2 to 4, as we see there. So our base in that for area number 2 is also 2 seconds, right? So don't just think it's 4 because it ends at 4, right? What's it in between? And then the height there is still 2 meters per second. So that's what we got there. Okay, our next triangle number 3, it's 1/2 times the base going from 4 to 6. So again, 2 seconds, and our height is still, oh, look at that, 2 meters per second. Okay, and then we have finally this big triangle down here. So 1/2 base, so base is going from 6 to 10. So that's actually a 4-second interval. And then the height, really important here that you note that the height is -4 because it's underneath the x-axis. So that is -4 meters per second. And those negatives make a big difference. Okay, so what do we got here? Don't bring out your calculator. You can do this all in your head. 1/2 times 2 times 2. 1/2 times 2 is 1 times 2 is just 2. Plus 2 times 2 is 4. Plus 1 half times 2 is 2 plus 1 half times 4 times -4. Well, 1 half times 4 is 2 times -4 is -8. Oh, look at that. 2 plus 4 is 6 plus 2 is 8 minus 8 is 0. Okay, so the displacement is actually 0 meters. They went back to where they came from. But that is how we find displacement on a velocity time graph. Just make sure that you are paying attention to what the axes are saying. So here we see velocity, here we see time. Okay, so that's only area situation we're going to go over. Now, when we're talking about this graph again, I just want to test you, make sure that you can tell the difference between this and a distance time graph. So I want to know on this graph, when do we have 0 velocity, when do we have 0 acceleration, increasing speed and decreasing speed. I'm going to give you a minute. Please pause and try to figure that out on your own. Okay, I'm assuming you all paused and figured that out. When do we have 0 velocity? So remember, this y-axis is now actually velocity. So the time we have 0 velocity is when it's actually, what? Right at 0 and goes through 0. So there's 2 points there where it goes through 0, and that's when we have 0 velocity at 0 seconds and 6 seconds. 0 acceleration, so that would be a constant speed. And constant speed means a horizontal line on a velocity time graph. Remember, this is not a distance time graph, okay? If we're talking about a distance time graph, there's no acceleration happening whatsoever because there's no curved lines. This is not a distance time graph, it's a velocity time graph. So from this 2 to 4 seconds here, we don't have any acceleration happening. We just have a nice constant velocity. Increasing speed, so that's when it's going from 0 up, or could be 0 negative. Okay, so we definitely know it has increasing speed from 0 to 2, right? It's starting at 0 and going up from there. But there's one other place where a lot of people wouldn't see increasing speed. But look at 6, it's at 0, and then it's technically increasing in speed, it's just going backwards. So 6 to 10, that is an actually interval in which it is increasing in speed, okay? Decreasing speed, when is it going towards 0? Well, here at 4 seconds it's at 2 meters per second, and then at 6 seconds it goes down to 0. So that's when the speed is actually decreasing. And we can break up that line like that. A lot of people want to think of that 4 to 10 line as one whole thing, which it is when you're looking at slope, but when we're actually looking at increasing speed, decreasing speed, we have two different things going on, so keep that in mind. One last thing is I want to translate this velocity time graph onto an acceleration time graph. So how do I do that? Remember, the slope of a velocity time graph is our acceleration. So that's what we're gonna look at. So I need the slope of this part, and then I need the slope of this part, which is easy, it's gonna be 0. And then I need the slope of, well, the thing is a lot of people will then go from 4 to 6 and 6 to 10. That's one whole line, that's the same thing. So I'm actually gonna find the slope from 6 to 10. So I have 3 different slopes here, and so that's gonna help me do my acceleration time graph. Okay, so we'll start with the slope from 0 to 2. I have 2 points on the graph there, so I have 0, 0, and I have 2, 2. So there's the 2 points I'm going to use to find my slope. Okay, so again, from 0 to 2, the point is 2, 2. My slope should be 2 minus 0, but that'll be my velocity, meters per second minus meters per second, divided by 2 seconds divided by 0 seconds, right? There's a change in my y divided by the change in my x, and that's just 1 meters per second squared, okay? So that's what we're going to translate for 0 to 2 seconds onto our acceleration time graph. Then there was this interval from 2 to 4, which is really easy. We don't even need to calculate that. What is the slope of that part? Well, it's a horizontal line. So that is just a slope of 0, okay? And then we have our final bit from 4 to 10 seconds. So let's look at my starting and ending point there. So here at 4 seconds, that point is 4, 2. And then at 10 seconds, that is 10, -4. Okay, so I'm going to use that. So my change in y should be -4 minus 2. My change in x should be 10 minus 4. Okay, so let's write that down. So change in y would be -4 meters per second minus 2 meters per second. And my change in x was 10 seconds down to 4 seconds, so minus 4 seconds. What is that? -4 minus 2 is going to be -6, okay? And 10 minus 4 is also 6, so it's -6 divided by 6, and that is -1 meters per second squared. Okay, so that I'm going to use these time intervals because it's an acceleration time graph. So the time should be on the x-axis because it is our manipulated variable. Time is always on the x-axis, okay, just so you know. So there's your time in seconds there. You should be using a ruler. Unfortunately, I can't here. My acceleration went from 1 to -1, so I really don't need too much here. So I'll say that's 1, that's 2, that's -1, that's -2, approximately. I don't have graph paper here, so I'm just estimating at this point. Okay, and then my time went all the way up to 10 seconds. So I'm just gonna go ahead and mark about every 2 seconds. So 2, 4, 6, 8, 10. Okay, so what did my acceleration look like? Remember, from 0 to 2 seconds, it was 1 meter per second. Squared, positive. So from 0 to 2 seconds, it just stays right there. Okay, and then what do we have? From 2 to 4 seconds, we had a slope of 0, so that was our acceleration, was 0 meters per second squared. So that's my acceleration from 2 to 4 seconds. And then we go back to 4 to 10 seconds, and my slope there was -1. So from 4 to 10 seconds, we're going to be down here at -1. I'm going to try to line it up here, and it's going to be going like that, and it's just staying. So remember, we're only ever doing acceleration time graphs where the acceleration's constant, so you'll only ever have horizontal lines. You don't need to join these lines or anything like that. It's pretty much telling us it's going from 1 to 0 to -1. And that's graphing. It's a big part of physics, but it's definitely not an easy part, so don't feel bad if you didn't 100% get that at this point. We'll be definitely going over more of that, but it's something that it's important for you to work really hard at, so good luck with doing questions.